So it's 3:30, we can start.
All right.
So good morning to everybody, good afternoon. I'm very happy to host here in this university, Professor Anderson Rocha from the university, well, actually the Universidade Estadual de Campinas, it's okay, from Brazil. It's one of the biggest technical universities in South America. So it's a really nice place to go if you want to go. And he's the head of the Instituto de Computação from the university, and he's giving us a talk about how to use the combination of artificial intelligence and digital forensics in the current year. He will present very interesting, challenging, so I will not go further in the presentation. It's being associated with many international journals and many committees for forensics, artificial intelligence, so I'm going to present him better than me, and he's going to present some of the new challenges that we are facing in digital forensics and cybersecurity. So I hope you are going to enjoy the talk as I usually enjoy his talk.
Thanks, Simone. So hello, everyone. I'm Anderson. I'm from the University of Campinas. It's called UniCamp, camp from Campinas. I'm going to talk to you today about AI and digital forensics, but this should be like a normal conversation. So if you have any questions, just raise your hand. You do not need to wait for me to end the presentation, okay? I've done a selection of 6 problems that we are developing in my AI lab in University of Campinas. And first and foremost, if you are in the PhD and you would like to visit us, our lab is open. It's very international. Indeed, I already hosted the students of Simone in my lab. So as part of your PhDs, if you want to do joint research, we are open. And the same is true from our students that are willing to come here. This talk should be given 3 years ago. It should be in 2019, but then we had this little thing called pandemic, and it was postponed. But it's very good to be here and talk to you about the research topics that we've been developing. Let me change my slides here to start. So just to let you know, I work as a professor in UniCamp for 13 years, and I work with AI for about 20 years, okay, since I was an undergrad. And to start with, I would like to mention, many of you have heard probably about the Industry 4th revolution, right? So Industry 4.0, everything being changed by the way that we do things now with technology and AI and everything. So this definition is very poor. So it was used until 2020 by many people to tell us that intelligence is now being part of everything. But now, from 1.5 to 2 years ago, there is a new definition that means that we are living in what's called the convergence revolution. So there are basically 7 technologies that you need to dominate or at least to know about right now. These 7 technologies, 2 of them are not very well developed yet. The other 5, they are called the technologies of the decade. So 2020 to 2030, you need to at least know these 5 technologies that I'm going to quickly give you an overview about. And there are 2 more. These 2 that are still developing, one is blockchain and the other is quantum computing. So these 2 are still in their early days, and probably they will like explode after 2025, quantum computing probably after 2030. But these 5 that I'm going to discuss with you, they are here right now. These are called exponential technologies because one accelerates the other. These are the GNR IoT AI. So G for genetics, it's the same for biotechnology, nanotechnology, robotics, Internet of Things, and artificial intelligence. So if you are doing engineering, you need to dominate at least one of these if you want to succeed as a successful person. If you are doing any other area, you need to at least know about these areas because everything rounds about these things right now. So let me give some examples. Genetics. Why are we living the genetic time? Biotechnology. The pandemic is here to show that this is true. Think about this company called Moderna. Probably you have heard of it, right? So Moderna was a startup before COVID-19. Of course, it was not a startup of like a few $1,000s. It was a startup of a few $1 million. But after 2 years of COVID, they are now listed among the 20 top companies in the world in terms of market valuation. So why is that? Because they developed a very important technology that was discovered around 2010, 2011. That's the addition of RNA. And to edit the RNA, which is the Cas9 technology, they are now able to find the vaccine for SARS-CoV-2. They are able to find vaccines for many other diseases. They are able to find medications. How do they find the exact position to cut the RNA to neutralize, for instance, the SARS-CoV-2 protein, the spike protein, AI? So they use AI to find the position. So it's one technology accelerating the other, AI accelerating biotechnology and vice versa. So this is the G of the convergence revolution. The second is N, nanotechnology. So everything that we know, it's miniaturized. So you have very small sensors that can now collect information about pretty much everything that you want, like smart dust to collect information about the weather. You have nanobots that you can swallow and they observe your body from inside. So this is the second accelerator, nanotechnology. If you go to the ground floor of any company, any industry now, you see a lot of robots. So they are doing all of the jobs based on automation. So this is this is the third component, the robotics, right? Connecting everything and sending the data to the cloud is Internet of Things, fourth component. And who processes all of this information? Who finds the patterns? The fifth component, artificial intelligence. So CRISPR-Cas9, the technology for editing the RNA, and now we have the CRISPR-Cas10, Cas11, Cas12, and many others. So now we can edit RNA in many different ways. Nanotech, the second component. Robotics, the third component. Internet of Things, the fourth component. And behind everything, the center of all, AI. So this is my area. Of course, I'm trying to convince you that AI is important, right? So 5 big areas, that's the convergence revolution. And there is a sixth, not yet fully developed, which is the quantum computing, and seventh, the blockchain. All of these 7, they are accelerating each other. If you want to read more about this, you can read the book, The Future is Faster Than You Think, from Peter Diamandis. This is like a mind-blowing book, really good, that will help you understand the moment that we are living right now. The future is faster than you think. This is the book. So speaking of this, we call this the 5th revolution, or the convergence revolution. And behind it, one of the components, as I said, is AI. So AI for us, at least for my group, is not related to philosophy, is not related to machines gaining conscience or sentience or being like smarter than us humans. Our definition for AI is basically an engineering definition. Okay, what is this engineering definition? It was given by Kaplan and Henley in 2018. It's basically any computer system that can collect data from the world, external world, process this data, learn about this data, represent this learned thing, represent this knowledge, and use this knowledge and capabilities to solve a problem and act upon the world, changing the world. And it's ideal, it's expected that this solution, this algorithm, this computer system adapt over time. Simple as that. If you can write a code that collects the data from the world,
You can learn from this data that you collected. You save the knowledge and you use the knowledge to take decisions upon the world, and you can adapt over time. This is for us, according to the definition, an AI algorithm. Okay, it's the full pipeline. So it starts with collecting the data, it ends adapting over time, acting upon the world. So it's more than machine learning. Machine learning is just the component that learn. AI is more than that. AI is like the full pipeline. So this is very related to what I want to talk to you today about the applications. Digital forensics is very intertwined with this definition of AI. And that's the reason I chose this as one possible application field for my research. Digital forensics is about, look again, collection of the data from the world. So external data collection, preservation, validation, identification, analysis, interpretation, and documentation and presentation of digital evidence, usually of criminal nature. So here you can see that we have the full pipeline of AI as well. It goes from the acquisition, the processing, the learning, the feature extraction, the knowledge extraction, the representation, the storage, the preservation, and then the presentation. So it's very related, and that's why I decided as one field of application of developments that we have. So in this research, I'm going to show you applications of AI, solving problems with AI, but the main application is in forensics, but it has other applications if you want to extend the technologies, okay? So think about this. This is an example of an election in the Netherlands a few years ago. One of the traditional problems in digital forensics was to identify if a picture was photoshopped or not. So when we had this problem, of course, by the time we needed to do this analysis, we were very involved in trying to identify compression, artifacts, illumination, boundary problems. When you cut and paste the pixels, you have like some inconsistencies. But the problems that we have in forensics now, they are much more complicated. So normally when we had something like this, like 10 years ago, Simone is here to prove it. Normally we did like some computer vision and signal processing techniques to identify like the illumination changes, the compression, and other things. The kind of problems that we have in digital forensics right now, we cannot solve them with signal processing and computer vision alone. We really need some hard techniques based on AI to help us to solve the problem, because it's a lot of data. So I'm going to give you some examples that are not just analyzing one object, one multimedia object. It's like a whole series of data points. So this is, we were happy and we didn't know. So, of course, we wanted to identify that it was a fake, something like this. But then it started getting worse. So here's an example of a terrorist attack in the marathon of Boston in 2013. So when you have something like this in forensics, what's the kind of thing that you want to do? The first, you have several different CCTV cameras that collect evidence a long time. So you have in different vantage points, and they have different durations, different point of views. So the first thing that we would like to do in terms of forensics would be, how can we combine the different views to have like something like a person walking, a virtual person walking, and we have a longer sequence of video to help us find possible suspects. This would be the first thing. So this would be computer vision and AI, combining different footage from different cameras in different times and different vantage points. So this is the first thing that we would like to do. The second, we would like to find the people that appears most, and those would be possible suspects that we could try to look more information about. So we would like to start with videos, something like this. And you have different vantage points. This is one camera from one vantage point, another. another. So a person with a cell phone walking, we could combine everything with techniques to have a longer sequence. And the idea would be to end up with something like this. After doing all of the analysis, we would like to have the suspects and ultimately to have the main suspect that's RNF brokers. So this would be what we wanted to do. So this study was published in 2014. If you are curious about, I can share the link later. But ideally, we should start with like the videos of the event, connect all of the points, like all of the dots, and have longer sequences of videos, and then look for possible suspects into the videos. So this project started a few years ago. It's now in the 6th year, year number 6. The name is Deja Vu. Deja Vu because we want to see again what's happened, okay? So it's a combination of many partners, and it's funded by the government of São Paulo in Brazil. And the research that we are doing, it's more than 15 years. The project itself, it's 6 years, but the research is like more than 15 years of research in terms of the techniques that we developed. So we have like a subject that we explore sensitive media, like child pornography detection in videos to help the police. Fact-checking fake news detection, digital manipulations, detect if a photo was Photoshop or not, detect who is the author of a tweet, for instance, or a social media post based on the content of the writing, finding the possible suspects in a video footage, that's what we call person re-identification, and connecting the dots of different videos in different moments of time, what we call space-time coherence. So I'm going to give you some examples of this now. The first one is just being published in Nature, like 2 or 3 weeks ago. You can just type in Google, user agnostic motion profile. What's the idea here? You are walking with a cell phone and someone comes and steals your cell phone. So our motivation was, if someone gets my phone, I would like this phone to be automatically blocked after the cell phone discovers that the way the person walks is different from the way that I walk. So the phone learns how I walk and it keeps validating me. So it's Anderson, it's Anderson, it's Anderson, then someone gets my phone. So if this person tries to use the phone blocks automatically and asks for a password. Why? Because this phone sees that the owner is not the owner anymore. Okay, so this was the motivation. This research was funded by LG, the phone maker, and it was just published now in Nature Scientific Report. So I'm going to give you the idea. So when you think about a person walking, what differentiates people? Do you have an idea? So people think that's like the size of the step or the strength of the step, like a person that walks like this. Or other people might think that's like how many steps you give in a minute. None of this is useful to identify a person. What we discovered is very, very different. So what we did, first of all, we received the signal that comes from the accelerometer of the phone, the gyroscope, and the magnetometer. So we have 3 time series. Based on this time series, we needed to represent in a very compact way temporal information. So what we did, we created images for each time slice. For instance, each second of data could represent like a few data points. So if you have a sensor that's 40 hertz, you have 40 points each second, but you can collect in X, Y, and Z directions. So if you create a window of size 1 second, then you have 120 points. So we create windows of like 4 seconds, 5 seconds. And when we put all of this information in time and you create an image about it, it's called a spectrogram, right? Some of you might have heard about this. So we create the spectrograms. And the nice thing is we proposed some ways of creating these spectrograms that when you look at the spectrogram of John is very different from the spectrogram of Mary. So when you look, you can see the difference based on the pattern that you are looking at, the texture. Because when you put this in a spectrogram, it looks like a texture, okay? So this is the first thing that we did. We call this hybrid image creation because we use 6 channels. A normal image is RGB. Here we create an image of 6. Why 6? Because I have a time buffer for the X, Y, and Z of one person, and then I can get the next X, Y, and Z, which can be from the same person or a different person. So if it's X, Y, Z of John, X, Y, Z of John, then a neural network will learn that these two sets of 3 come from the same person. If it's a different person, XYZ of Mary, XYZ of John, the network will see the difference in the 6 channels. So when we do this, we also can combine over time, and then we are able to separate the people. But we are not using all the frequencies of the data. Here's an example. The first thing that we discovered. Normally, all the existing data sets, they collect the data in the same day, the same conditions, and this doesn't work because we discovered that it's very hard to identify a person if they change shoes, if they change clothes, if they get hurt, so they will walk differently. If it's a woman or if it's a man, it's gonna be different. So here you can see an example. The purple one on the left is the training data. And the yellow one on the right is the test data. This is terrible because they are not overimposed. So if you really want to have a good distribution, training and testing data should be overlaid. So now we needed to have some kind of transformation to deal with what we call domain shift. So that's why we started investigating the first attempts. Here's another user, very different data from training and testing. So this is not good. We did a lot of transformations until we realized that we needed more specialists to help us. So who is the better, what's the better group, the best group to deal with motion? Any idea? So if you think about people in our careers that deal with motion, who is this group? What's the kind of profession that understands the best in terms of motion? Dancers. So I did a partnership with a dancing group in Canada, McGill University. And we put a lot of sensors in the different joints of these dancers to understand the motion and to isolate the part that was really helping to identify a person. And here's an example. We did this partnership with them. We collect the data set, it's public. And here is the points that we put the sensors to understand the motion. We also put the MCU here, which is a very good sensor. We put an IMU and we put the cell phone. So the dancers needed to do all the dancing with these different sensors. And the idea was, okay, after we do this, how can we identify a person? What's the difference between A and B? And we collected all of this data in different days, different clothes, different shoes to understand what was going on. And here is the examples of the projections for the different sensors, FTC, FLE, FACS. They are sensors in different parts of the body. And the first thing that you can see is that depending on the part of the body that you are, it's going to be a completely different region in the projection space. And now we isolate the frequencies that allow us to separate A and B, for instance. And here you can see that the training and testing, they are overlaid, so it's good. We discovered the right frequencies and nobody was dealing with these frequencies before. Everybody in the literature tries to identify a person based on what happens in the frequency of 1 to 5 hertz. So they look at the step, they look at the strength, but we discovered that what differentiates you from you is what we do like this. When you walk, you have a very tiny motion in the waist. So it's like this. These motions to the sides is what separates people. And this happens in the frequency of 6 to 10 hertz. So when we isolate 6 to 10 hertz, we differentiate the people. And here's the group. When is the same person? When is a different person? And the brighter one is training, the darker one is testing. Overlaid as we wanted, separate the groups as we wanted. So this is the results. So now we have a technique to separate people. Of course, it's really good for some people. Some people are really easy to separate, and others are really hard. What does it mean in terms of numbers? For some people, I can separate like 99% of the times I know that John is John. But there are other people that in 55, 54, 52%, that's the accuracy of these people. For these people, I give up. I cannot separate them because they always walk in a different way. And another thing that we discovered is that we only can authenticate a person if they are walking by themselves, if they are alone. What happens when you try to authenticate a person that's walking with another person? Do you know? If I try to walk with Simone here, why I can't determine who is Anderson and who is Simone? Because we synchronize our walking. It's not going to be me or him. It's going to be the synchronized walking of us both. So we discovered this as well. Okay. And here is like what we do in each of the steps. We start counting when the person puts the toe on the ground and then changes and then puts the toe off. So this is the complete cycle of walking. This was the first problem. Just publish it. If you are curious, you can look online or send me an email where I can share the text with you. The second one is very recent, just being presented in a conference this year. Some years ago, after Trump's election, we saw a very big problem. So a problem of misinformation. And 2016 was indeed the year of post-truth. And that's when we started doing research on fake news identification. So naively, very naively, we thought that we could develop a neural network that could receive a piece of news and could classify at the end if it was fake or not. We did some research. The accuracy was good in the existing data sets. It's like more than 90%. Then we showed to the journalists. And they said, no, in practice, this is useless. So you know what the researcher does when someone tells that his research is useless? He tries to understand why that's useless and try to do something that's useful. So first of all, we discovered that, okay, we cannot classify a piece of news as fake or not, because it's really hard. It's a really hard problem. So we asked the journalists, okay, what would be useful for you? And then they said, we never receive a piece of news and classify the piece of news as true or fake. This is not possible. What we do, we decompose the piece of news into claims. And for each claim, we try to fact check. We try to check if that claim is true or not. So that's when I recruited a student to do a PhD with me to try to solve this. We are still in our beginnings, but we are in this direction. We receive a piece of news, we decompose into claims. For each claim, we create some questions automatically using AI. And then we go online, try to find the answers to those questions, and then we check consistency. When it's inconsistent, we raise a red flag for a human to take a look. Okay, this is what we are doing. So it goes like this. In the beginning, it was like this. We received the post or the piece of news, and we tried to, okay, this is a network. We tried to decide if it's true or not, but the journalists didn't like this. So we shifted. This is what we did in the beginning. We received the piece of news. We went online, got the comments about that piece of news, and also we went to social media and got the posts about that piece of news. And the idea would be the network to learn the inconsistencies. So suppose that I publish something, suppose that it's a news article, then I put that news article as the input of the first branch of the solution. Then I will go online and get all the comments in that publisher about that piece of news. And someone might be telling, oh, this is fake, oh, this is not believable. So it goes in the second branch. And then I go to the social media and I get that piece of news and I also get the social media posts about it. So people might be telling that it's a fake. So the network would learn these inconsistencies. In theory, this is good. In theory, it works. Why doesn't it work in practice? Because people in practice, they live in bubbles. So when a person reads a fake news, that person really believes that's real news. Like in Brazil, we have a president that's called Bolsonaro, and it's like a Trump. And his group is really like believers. They're not reasonable people, they are believers. So no matter what he does, they believe what he's doing. So if he publishes something, even if I prove that thing is fake, his believers will say that's true. So this network would break in that case because I would put as input the text that's related to Bolsonaro's group. And then normal people would go there and say, oh, this is fake. But then his believers come and they say, no, it's not fake. I believe, oh, it happened to my aunt. She took hydroxychloroquine and she's good now. Oh, that happened to my father. He got like ivermectin and he is healed of COVID-19. So you have the people discussing, one group saying that's true, the other group saying that's fake. The network would be lost. So this is why we shifted our gears to something different. So we learned what's the normal pipeline of a journalist. It starts with like choosing the claim of a text. Then with that claim, it's assigned to a team. This team goes and verifies the claim to check if it's true or fake. Then when this team puts together all of the claims, this team can create a report about fake or not. Okay? So this is what we wanted to do, to help the journalist in this pipeline. So this is something that we do. It's called XAI, Explainable Fact Checking, because it's explainable artificial intelligence. We start with a claim. For instance, here, example, Lee MacPhail passed away at his home at the age of 92. This is the claim. Then I go online and I check what's possible to find about this claim. So I go to Wikipedia, which is our source. MacPhail lived in Delray Beach, Florida, where he died November 8th, 2012, at his home. He was 95. At time of his death, he was the oldest living Hall of Famer. Okay, now I decompose both. I decompose the claim and I decompose the evidence into questions using like natural language processing techniques. So I do some questions like that automatically. How old was MacPhail when he died? Where did MacPhail die? Things like this. Then I use also AI to answer that. So the first answer for the claim, the algorithm says 92. Then the algorithm answers the question based on the evidence, 95. So now I see some inconsistencies. I tag this message as doubtful. Okay, so this is just the beginning. We just published a conference. It's not even a journal paper yet. We now just did a partnership with a journalist group in Germany to extend this. But this is the idea, to decompose a news piece into claims, check each claim, create questions about the claims, and check consistency. Okay? And it also gives the importance. If you look at the very right, you're going to see a number. This number is the importance. The algorithm learns what's more important in terms of questions. It's not perfect. It's far from that. The algorithm is now creating some repetitive questions sometimes. So some questions are exactly the same, just paraphrasing. So we need to minimize that. It's normally answers correctly. So it's the main problem right now is creating the same questions. So similar questions. So we want the algorithm to be more diverse. So this is what we are investigating. All right. So this was the second. You control the time, okay? So the third problem is this. A few years ago, I was reading some newspapers, and there was a claim that I found shocking. About 5 to 10% of research in biology and medicine is fake. 5 to 10% by that time, way before the pandemic. 5 to 10% of the research in biology and medicine had some kind of forgery. It could be in the content, it could be in the text, it could be misleading, or it could be an error. Okay? It could be like the person wants to do it, or it could be like the person does not even know that there is an error. But it was 5 to 10%. So it's shocking because every 10 papers, at least one will be fake or contain false information. Remember, this was before COVID-19, because with COVID-19, this was multiplied. So that's when we did some effort to start research about this. This was 2016, and we've been investigating this since then. We just had our major first paper accepted. Was accepted recently in Nature as well, scientific reports. And the idea here is we want to focus only on the images. So if there is a paper, we extract the figures, and we want to check if the figures were modified or not. We don't look at the content, we don't try to understand the text, it does not matter for us. We only look at the images. For us, what's important? Pixels, okay? So this was our motivation. So here's an example. This is an image from a microscope, from gel. And here's the thing that people do most. They have the result on the top left, but they need more evidence that their method is good. So what they do, they go to Photoshop and they start multiplying the good parts of the gel that was showing some conclusion about their work. So they change colors, they copy position of the pixels, they copy from one image to another. So this is a very old problem in digital forensics, but now applied to science. So what we wanted to do is to, first of all, check if the algorithms that we developed for natural images, if they worked. Turns out they don't, because it's a different kind of image. The digital forensics methods, they are normally developed for natural images, RGB images, like outdoors, indoors, doesn't matter. Here, these images are of different nature, so we need to adapt the existing algorithms or develop new algorithms for this kind of thing. So this is what we do. We go online, we get a PDF of a paper, we extract the images, all of the images of the paper, and then we separate each piece of the image and try to see evidence of tampering, evidence of manipulation. After we do that, we also get the authors' names. For each of the authors' names, we go and get their papers, published papers that are online, also extract the images of those papers and try to find evidence of like reuse of images. Okay, so we create a graph. Turns out that we have this concept called paper farms. What is a paper farm? As the name says, it's a place that you create papers, but not in the nice way of it. It's like raising papers, like creating pigs. So the authors, they join like 10, 20, 30 authors, and they do mainly two things. One, they cite within the group. Those images as new research. So they always keep publishing, but always fake research. One famous case of this was recently discovered in Elsevier, the publisher. They discovered a paper farm in India that had like hundreds of papers. There was another in China, hundreds of papers. And one famous case about this is from a South Korean, very good scientist. We don't understand even now why he did this. He claimed a few years ago to have achieved 11 cases of success in cloning, human cloning, or organs. But then someone, when the paper was published, I think it was in Science, someone tried to replicate the results and was not able to. So this person asked for an investigation. And after an investigation, they discovered that only 2 cases worked, only 2 cases of the cloning that he claimed it worked. The other 9 were clones, but Photoshop clones, not like real clones. Okay, so this guy was dismissed. He's not a professor anymore in South Korea, but this is an example of what I'm saying here. So this is what we have been doing. There's a lot of research yet about this. I hope to have more results soon. There's time?
15 minutes.
15?
15.
Huh?
15, not 50.
15, okay. So this is the other example that I would like to discuss with you. Normally, when we think about machine learning, the decade of 2010 to 2020 was basically about supervised learning. So we had very good examples of techniques developed to solve problems based on labels that you had of a training set, like discovering what's the kind of object that's in an image, discovering the face of a person, who is who, like John is John, Mary is Mary, based on the face, many things successful, even for automation. But the decade of 2020 to 2030, it's about focusing on learning without labels. So unsupervised label is the holy grail now. Try to extract information without the labels, because this is the kind of information that we have. This is the kind of data that we have. And it's expensive to have labels. So here's an example of a problem that we have been focusing a few years already. It's try to do self-supervised learning. So I don't receive labels. I try to teach the algorithm to teach itself. Okay? So we started with this problem called person re-identification for a reason. It's not biometrics. The problem is in biometrics, but our reason was we need to have a very difficult problem in order to see the power of the self-learning. Why difficult? Because in person re-identification, we are talking about identifying the same person that appears in different cameras, in different moments of time, different illumination, different positions. So this is a very hard problem. Why? Because normally, if I want to identify, for instance, this object here, it's a rigid object. If I take a photo from that camera and a photo from that camera, it's a rigid object. So like the problems in the classes in ImageNet, normally it's easier because you have the labels, many objects there, they are rigid. This is not what happens when you're talking about people. It's deformable, you can change the clothes. If you're walking, the illumination will change the color of your clothes, it changes. So this means that it's possible that I have images of myself in my cluster that are more different than a picture of myself and another person. It's very likely. So if I'm wearing gray and I'm a Caucasian, it's possible that there is another cluster of a person, Caucasian, wearing gray that's more similar to me than another image of myself under the sun. So this was our motivation. And here's an example. The first identity, we have changes in point of view, pose, illumination, occlusion, background. We have no annotation nor side information for anybody. We only have the suspect person. This is an image of the person that I'm looking for. And everything else is images that I want to check if it's from the same person. Okay? So our method is here. This is very new. We are going to submit this paper tomorrow to Transactions on Information Forensics and Security TIFs. So what's new about this? First of all, is the way that we learn. When you try to find a cluster, normally the people that try to solve the problem of clustering, they try to decide what's closer based on a distance. And below a threshold, I can say that's from this cluster. This is normally what's done. First of all, what we didn't want here to have a threshold. We don't know the threshold. I don't know the distance, the minimum distance from this image to that image to claim that that image is from the same person. I don't know. And I might have a person here that's closer to myself, but it's from a different identity. As I don't have labels, I cannot control that. So I wanted something that was independent of this kind of thresholds. The second thing is not everybody uses the context. So what we wanted to do here was something related to social networks. So how social networks work. If I know someone and that person also knows someone, there is a chance that that person knows me or vice versa. So I use the context. So if this image is close to me, this image is close to me, and it's me really, and not another person, I need to check the neighbors of this image and the neighbors of myself. So I have two sets of neighbors. But if really that image is from me, that image should be closer to other neighbors of mine, because those neighbors of mine are really me, right? So suppose that I have Anderson and image 1 and 2 from Anderson. Because of a previous iteration of the algorithm, I tagged them as possibly me. So I have image 1 and 2 of Anderson. So these are my neighbors. Now there is a candidate here. How do I decide that this guy is my neighbor? I don't have a threshold. So I look at the neighbors of this guy. Suppose that his neighbors are these two images. Oh, this guy is neighbor of my two neighbors. So there is a likelihood that this person is myself. So I decide that. But this idea was also, there was also another thing that we could do. I could take this decision only based on this iteration that I am at, and everybody does that. Or I could use the history. So now I have the physical neighbors and also the neighbors over time. So in iteration 1, this image is neighbor of Mary. But in iteration 2, iteration 3, iteration 4, this image is not neighbor anymore of Mary. This means that in the beginning of the algorithm was not so sure, and that's why it thought it was a neighbor of Mary. But in the subsequent iterations, it refined his knowledge, and it's not Mary anymore. So we keep track of all the neighborhood lists. So this changed a lot our understanding of the problem. So we have the idea of temporal neighbor and physical neighbors. So these are the two main things that we brought to this problem that allowed us to learn identities automatically. So everything based on the context. And third and last thing, it explains why it takes a decision. So it has a mechanism of XAI. So here's an example. The top left is the identity that I'm looking for. So after the iterations of the algorithm, you can see that it found a lot of neighbors, and it's the same person. And it justifies, why is this person? Because the backpack is present, the purse is present, and the shoes are very, very characteristic. So when you have something that's working That's the behavior. And the nice thing is when you have something that's not working, first of all, normally it's not from only one person. It's when the detector put two together, for instance, and then the algorithm does not know. And the second thing, look at the maps that we have. So when the algorithm gets it wrong, it's more spread. When it gets it right, it focuses. So now we can even extend this method to post-process the hitting map and see if it's a case of failure or success. We still don't have this module, but when we look at the results, we see that it's very clear when the algorithm is wrong and when the algorithm is right. So we don't have time to continue, but I had another problem, that's the authorship. So if you are curious about, you can send me an email and I can share with you later. Just to, I have 5 minutes, yeah.
No.
Okay. So the 5 minutes, here's the challenge. Suppose that you want to identify the author of a book. Now, with the technology that we have, this is very easy. You have a lot of data about the author, and you can learn the behavior, the stylus of that, the stylistic features of that author, and it's okay. Unless it's like a very difficult author like Fernando Pessoa, the Portuguese author that uses several homonyms and each one writes in a different way, so the algorithm would break, okay? But suppose that it's not Fernando Pessoa, you could do that well for different authors and books. If you were dealing with emails, pretty much the same thing. You have a lot of data, you can learn the behavior of a person, and you can identify the author. But if you have short messages, 140 characters of Twitter, like in a tweet, it's very, very, very hard. And of course, if you want to do nice research, you choose the very, very hard problems. So this is what we wanted to do. Identify the author of a post of a short message based on the content. Okay, so this is what we did. And more than that, we were not experts in natural language processing. So what we wanted to do was to transform the problem of identify the authors of a message into a signal processing problem. And we did that. We transform a text. This was before transformers, okay? Before BERT and everything when we started. So we transform a text into a signal. And when we do that, it's very good. Why? Because with signals, you can do convolutions, you can do all of the operations that we can do normally with images and signals. And that's when we were the first group to publish in a signal processing conference a paper about text, because we transformed the text into signals. And since then, we developed a lot, this research for authorship. We have we transformed the text into signal. We developed like the first idea of a transformer a few years ago. Now we extended this with transformers as well. And we have the interpretability. We show in the text what are the stylistic features that allow me to say that this tweet is yours. And for that, we use something called line, which is a module to understand what happens in a text-related problem. And here's the nice thing about this. Using this technology, we compared our solution to one that was published a few years ago, and transforming the text into a signal improves the result in more than 6 percentage points. So it's nice to see a text understood as a signal. So this is it for now. And to conclude, what I would like to say is in this area, we have many problems. We normally need to adapt continuously. As you've seen, a lot of times we have information that comes in time. Conditions that are dynamic. We have biases that we need to detect. It's an open set problem. We don't know the labels. And for all the things that we are doing, we try to have explainability. So this is the XAI module. Sometimes we have big data, sometimes we have small data. The sensors are of different kinds. That's why my lab's name is Reasoning for Complex Data. It comes from different sensors, record. Sometimes these sensors will fail. Sometimes the sensor will not give you high quality data. And sometimes we are going to have missing variables. So this is the interesting things that challenges us, not only in forensics, but in general in machine learning and AI. And with that, I would like to show you a small video of the new generation, the new reality that we are living, that's called the synthetic reality. Have you seen this? This is DALL-E, a transformer that creates content based on the description. If you have that, this is the new frontier for forensics. How can you detect that this is a fake? So this is something that definitely needs to be in our proposal next year to deal with this kind of problems using AI. Like cute cat, okay. Look at this. It was a dog. Then you just type cute cat and it automatically selects what's there and puts a cat. If you just see the image, how do you know if that's not a photograph? And then if you see a photograph published in a paper, in a newspaper, how do you know if it's really something that happened? So now more than ever, an image is worth 1,000 lies and not 1,000 words. And this is another one. This is Morgan Freeman telling us about the synthetic reality. Do you have sound in there?
Oh, yeah.
Can I use this sound? Let's see.
Here, yeah.
No.
No way. You have sounds.
Yeah, should have. But I don't have the control of the audio. Perhaps you need to. No. You should control the audio there.
No, the audio is not coming because we don't have audio connected.
Okay, so 1 minute.
Same as speaker. No, speaker, yeah.
That's the speaker, right?
Yeah, go for the speaker.
Okay, let's see. No. Okay, doesn't matter. This was to show you. This is on YouTube. You can type later Morgan Freeman synthetic reality. And everything that he says here, it's synthetic. He is synthetic. His voice is synthetic. Okay? So if you see something like this, how do you detect? This is like deepfakes 2.0. Deepfakes is a process of creating fake content. But the first generation had a lot of problems like texture, eye blinking, and things like that. You could use lips, you could use to detect. But now it's much more complicated. The latest example was in American Got Talent. Probably you have seen that. 2 or 3 weeks ago, a guy went to the stage and he started singing, but in the background, who was singing was Simon, the presenter of American Got Talent. You can see also on YouTube, and it's really, really good. So when you see something like that, how do you detect it? Recently, another news article was saying that many people are using deepfakes for job interviews online. Yeah, they create deepfakes like a younger, nicer person, like a Brad Pitt, and they do the interview like for remote jobs, just because they think they have more chances. And it turns out they do. Why? Because people have a lot of prejudices. If you're black, for instance, you have less chances of being hired because people have prejudices. So these kinds of situation will multiply. So how can you detect forged content? This is the challenge that we have. DALL-E 2, other contents, this kind of content, this is something that really shows us the need of AI to help us identify. So in the end, where we want to go, we want to find solutions that are ethical, that are just, fair, understandable, and that we can audit to understand what's going on. So this is the University of Campinas, and I thank you for your attention, and I can answer some questions. Thank you.
Are there any questions?
Remember, if you want to visit us for some like 1, 2, 3 months, we are open.
I have one question. In the meantime, you think yours, okay? Is that I've seen that in the fake news checking, you do the decomposition, that you do the checking of different statements. What about the detection of resonation chambers? So there are some methods doing fake news that aims to detect how the information spread, because it is pushed forward by believers, as you call them. Basically, this is going to spread with a different pattern with respect to a standard news. So,
well, the main thing is it's very hard to do research with fake news or fact checking if you are not one of the big 9. And for those of you that don't know, big 9 are the big 9 companies that pretty much control everything that we do: Facebook, Microsoft, Tencent, Alibaba, and others. They are 9 in total, and they have enough data to do this kind of analysis because they can create these complex networks, and they can analyze the flow of information. They can analyze like the big nodes and things like that. So when we started doing research in fact checking, we had 2 options. One was based, okay, can we create the network? If we could analyze like patterns of diffusion, echo chambers, and things like that. If you don't have a partnership with one of these companies, you cannot do that. So the other path that we had was, okay, let's start just based on the information, and then we can try to analyze the information without the nodes associated. So if you are like small, like we are, just researchers without the big 9, this is one thing that you can do, or you can partner with them to try to have the nodes information. We don't have anything related to echo chambers because we would need the social network around it.
other questions?
Just out of curiosity, when you talked about people using DALL-E and Link or something like that, something like similar to that software for hiring processes, I wanted to ask about, is that easy to use for like the everyday person to actually, is the software already built in? It's already set up for everyday use?
Well, let me give you 2 examples. 1 year ago, or 1.5 years ago, there was this app called Face App. It went viral. I don't know here in Italy, but in Brazil, everyone was using it. It's an app that you download, App Store or Google Store, and it can make you younger or older. So people just downloaded it, and to download it, you needed to accept the terms of use. And what's the terms of use? You give access to all of your photos. So there's a company from Russia, and in like 3 months, this guy had one of the biggest database of faces out there, because a lot of people download their app and they were using without reading the terms. So easy to use, pretty much anyone can use. Another one is to create deepfakes. Now there is a strong willingness to ban deepfake apps, but you can still find some. You can just download, you put a photo of yours, and it creates the photo that you want. It's like a mapping. The definition that I use for deepfakes is like molding that molding messes for child. You give the children the Play-Doh and they can do a lot of things with the mess. It's like this with the faces. You can move things around, pixels around the face, and you can make any face like others. So easy to use, but now there is an enforcement to ban this kind of content. What about DALL-E-like? Right now, there are websites that already use that. You can just type the things that you want. But normally what they do right now, it's like simple things in terms of the consequences, like a polar bear playing basketball, or like an animal flying around the moon. Right now they enforce this kind of thing. But think about this. We are just in the beginning. And the quality of the images are already very, very good. What about like 1 or 2 years? These tools will be freely available because inevitably they will be available. It might be either because the companies decided to do so and then people try to modify it, or someone can train one. It's not very hard. Right now it needs a lot of processing power to do things like that. But in 1 year, 2 years, I used to give the example of the man on the moon. You know that the computer that did the calculations to send the man to the moon was like the size of this room or bigger? And do you know that this thing here has more processing power than that computer? And it's like 40 years, 40 something years. So I think that in a few years, these kind of solutions will be freely available like an app. And
my next question would be just about the 6 problems, 6 issues that you introduced to us. About seven. The 7 problems. Which one would you believe to be the most problematic in the next future, and which kind of issues that would be applied to forensics as for criminal investigation, and finally, how would you solve it?
Very hard problems. About the problems that you mentioned, or about the accelerating technologies that introduced?
Well, basically it's more about the problems.
The problems, okay. So just about the accelerating technologies, definitely the most complicated one is biotech. And you know why. You can edit genes, you can generate a person the way you want, you can create superhumans, you can create like a different big gap between who has the money and power and who does not have the money and power. So that's definitely much more complicated than the impacts of AI. Okay. About the problems that I mentioned here, the most important one, I guess, and I need to put that in the project as well, is how do you trust content? Because we live in the information age, but if you cannot trust what's out there, what do you do? So if everything that you read, everything that you think, that you see is fake or can be fake, what do you do? So it's gonna erode democracy, first of all, because you will elect people based on false information. Any kind of information that comes to you from the state, for instance, will be likely false, and then you cannot claim anything. You cannot trust people. So we erode the way of life, the social fabric of like society. So I think the most important problem is content trust. And this can be related to fake news. This can be related to deep fakes. This can be related to synthetic reality, all of it. Thank you.
Currently, what you are working on, like in what kind of project, or what will be like the next one?
Okay. All of these problems that I mentioned here, they are not solved problems. So we intend to continue to investigate them, especially this one about the content quality, the trustworthiness of content, deep fakes, things like this. But now we also are investigating something related to not in forensics, more in health and well-being. Our lab is dedicated also to try to transform medicine from reactive to proactive. So we selected a few diseases that we think that sensors, because I mentioned about the sensors that can collect different kinds of data, so that we could use these sensors to anticipate problems. Example, I have one student working on detecting sleeping quality. So if you cannot sleep well, it's likely that you're going to have problems. So sleep quality, we also are working with identifying sedentarism, but not sedentarism in the way that you think of. Sedentarism is not that guy that just stays sit all day. That guy, we already know that he is sedentary. What we want to identify is what we call sedentary behavior. It's that guy that walks 1 hour or runs 1 hour a day and thinks I'm an athlete. And then this guy sits for 10 hours straight. This guy has the same likelihood of developing a problem than the sedentary one. So we want to identify what we call sedentary behavior. And we are doing that with smartwatches. So we put a person to wear a smartwatch and then we collect information along the day. Another information that we want, another disease that we are looking at is diabetes and metabolic diseases like high pressure and things like that, because we can identify with the motion of the hand putting something in the mouth, we can identify that the person is eating. Then we activate a sensor to measure the amount of sugar 15 minutes later, and then we can calculate the glycemic curve of that person. So we can try to anticipate if this person is developing like high sugar rate in the blood. And this can be an indicator of diabetes, but way before it becomes reactive. So this is something that we are trying to start. We started in January this year. It's gonna take a lot of time, but we hope to have some information, some advancements in this regard as well. I think that we have questions from the audience.
Actually, I just.
Oh, it was you. Okay. More questions? No?
I have a question about the problem of the identification of person by their movements. If you move the problem into the problem of image recognition or image comparison, right? I was wondering if this approach, I mean, I can understand the reason because there is a lot of literature, there is a lot of experience about image recognition and comparison, but do you think that we really need to go like this?
No.
Or
no, we don't need to go in that direction. There are mainly two reasons for that. One is that I'm more an expert in images than in signals when I started. But now, like 5-6 years later, I know a lot of signals as well, and we are working with directly with designing the networks for signals. This was the first reason when we started in 2015. And the second reason was that we didn't have the power to process those signals in time in our machine. So when we transformed those signals into images, like a lot of minutes could become just a few images, and it was easier to train. So these were the two reasons. But now we are dealing with directly with the signals, and the results are pretty much equivalent.
because there can be biases coming from the image world.
Oh yeah, we have some problems when you transform the signal. You lose some locality information that you have when you work with directly with the signals. So right now we are processing the signals with transformers, and these are much better results than when we do with CNNs.
Sorry, but I just want to take the chance to ask your opinion about the problem that I was starting to think about recently. Let's say there are some images, some kind of images, so just for instance, one single image. I want to be sure that even if it gets updated or uploaded online and shared multiple times, I want to get some software or just a technique thanks to artificial intelligence or some kind of similar implementation to always get that image, I don't know, maybe blurred or automatically taken down. Do you think that there could be a chance about, for example, contacting maybe Facebook or the social network providers and stuff to actually implement some software allowing this reproducibility to get blocked? I don't know if I explained.
Let me phrase your question. You are looking for something that could detect some kind of content online and blur it, right?
Exactly.
Yeah. My opinion, I repeat, this is my opinion, is that probably this network will not do anything for you. You are too small of a person to deal with these guys, and there is an excellent book about this kind of thing by Shoshana Zuboff. She is emeritus professor in MIT. It's called The Age of Surveillance Capitalism. And in this book, she discusses a lot of these things. What can we do as a society to push these companies, these big nine, to help us and not like just look for profits? So we had a problem some years ago that was kind of similar to what you're mentioning. We were approached by this company, a small company called Samsung. They wanted to do this. We want parental control. So we want a parent to buy a TV. This parent goes to the setup of the TV and automatically blocks violent and pornography content. And so the children will not watch them. So they asked, is it possible that we contact the providers to do this? And we checked it, it was not possible. So they decided, okay, so you need to do that at the endpoint. So you need to do that at the edge. And then we developed the algorithms to do that in the device. So we embedded the software in the core of the operational system so that any kind of stream that arrives, we block if it's violent or pornography. And we do this in real time. It's implemented now in smart TVs. If you probably have smart TVs with parental control here, if you look at the options, you're going to see the lab that did it. It was our lab, smart parental control based on sensitive content. But we could not do with the providers. We needed to do on the edge, on the device. It would be very nice if the providers could do that online. And there is now a very big effort to do that with children pornography. With child pornography, the providers are interested in blocking. So they calculate the sensitive hash of images, and anything that's reported to be like child porn, the system already marks it and calculates for everything else and compares. This work is coordinated by a friend of mine, Honey Fried, professor in the University of California, Berkeley, but it's only for child pornography.
So it's a matter of legislation for child pornography is banned most countries.
Yeah, pretty much it's banned everywhere that I know of.
They have different types of regulation depending on where you go, so it's not easy.
Yeah.
If I'm Netflix and streaming from California to all around the world.
Exactly. Any other question? So guys, once again, thank you for your presence. If you need anything or are curious about anything that I showed here, just hit me through email. Okay, thanks.
Thank you very much. Oh, sorry, there's a question. Sorry.
There's a question, okay?
No, we have not. Have you quantified the impact of quantum technology in digital forensics?
The impact of?
So I read it. Okay. If you have quantified the impact of quantum technology in digital forensics, and what do you think is going to be the drawbacks and the benefits?
Wow, that's a hard question. First of all, I'm not an expert in quantum computing. So everything that I'm gonna say is, I think. Okay, so I think the impact is gonna be like it's turned everything upside down. So quantum computing will turn pretty much every technology that we have nowadays upside down. You can think about banking, about the algorithms they use, RSA, it's gonna be broken. About the algorithms to create content, fake content, they will be very, very faster. So our work will be multiplied, but of course we can also use the quantum computing technologies to detect this kind of things. So it's very early to say to measure the impacts, but I think it's gonna be a challenge.
Okay. No other questions from chats?
All right,
So
so now thank you.
thank you again. And we are finished.